All right, so in this video, we're going to take a look at a couple of theorems here. The first one being is a theorem NI from our textbook. So what this theorem states is, okay, okay, so theorem NI. So what this theorem poses is that non-singularity implies invertibility. Okay? Or non-singularity is invertibility. So all those are equivalent statements. So the theorem states that, okay, if A is non-singular, again, and A being a square matrix, A is non-singular if and only if, so an equivalence relation, if and only if A is invertible. Okay, so again, that if and only if a much stronger statement, so we need two directions to prove this here. So the first direction, let's say that we're going to prove the statement if A is invertible. Then A is non-singular. All right. Okay, so A is invertible. That means that there exists some matrix here, A inverse. So it's invertible, right? That I can find it, such that the product of A and A inverse is the identity matrix, right? So this is by definition, right? This must be true. By definition of matrix inverse, MI. All right, so this is our hypothesis. So we are just stating our hypothesis here. All right, well, from our previous theorem, from theorem NPNT, from the first video in this module here, so I know I sub n, the identity matrix, is a non-singular matrix. So theorem NPNT tells me that A, in this case, and A inverse, both of those, but the theorem just asked me about A and A inverse are non-singular. Okay. All right. So that one's it, right? That one was quick in this direction. All right. Now let's take a look at the other direction. So here we start in the other side, right? If A is non-singular, then A is invertible. Okay. All right, so here, let's start with our hypothesis here. If A is non-singular, what does that mean, right? If A being non-singular, that means that I can reduce row echelon form into the identity matrix. All right, so that means by construction here, right, we have a theorem that tells me how to find an inverse. Right, if I concatenate A and the identity matrix of size n, again, A is a square matrix, right? So I can reduce row echelon form, and since A is non-singular, I'll get the identity matrix here and some matrix B here. All right, but then this implies that AB is going to be IN, right? That's from construction of a matrix, right? That's what this, of an inverse matrix, right? That guarantees me that. But our previous theorem, the OSIS, also states that if that's true, then BA is equal to IN. In other words, by construction of the matrix, A is invertible. All right. Okay, so this kind of gives me now another property of non-singular matrices, and I'm going to add them to our next theorem here, which I won't go into the proof here, but I do want to discuss here because it's a theorem that we have seen before, but now we are adding to it. All right, we're going one more round here with our NME theorem that list non-singular matrix equivalences, right? So theorem NME3, non-singular matrix equivalences. So it says, suppose that A is a square matrix of size n, the following are equivalent. A is non-singular, a row reduces to the identity matrix, the null space of A contains only the zero vector, and A, again, equal to the zero vector. The linear system has a unique solution for every possible choice of B. The columns of A are a linearly independent set, and now we're going to add to that. A is invertible. Okay, now, when you see this, what you want to get from this is that this is not telling me 6 different theorems. This is establishing equivalent relationships, equivalence relationships. So what that means is that if you know that one of these things are true, so if I tell you, for example, that A is non-singular, then all the other 5 properties hold, right? So it's just telling different ways to describe non-singular matrices. All right, so if you're like, the matrix is non-singular, a row reduces to the identity matrix. It has a trivial null space. The columns are a linearly independent set of column vectors. A is invertible, right? All of these properties are equivalent ways to describe a non-singular system. Okay? And then more importantly, right, using this, that kind of leads us to that theorem here that you see right below it, SNCM solution with non-singular coefficient matrix. And it says, suppose that A is non-singular. And again, really we're just using these NME kind of equivalences along with matrix multiplication, matrix inverses, etc. to show that. Then suppose that if A is non-singular, then the unique solution for LSAB is A inverse B, right? So it's a way to find the unique solution to the linear system, right? So here, what that means here, oops, if A is non-singular, then the unique solution, right? And it has to be unique, right? Because the theorem NME3, unique solution to the linear system A and vector B is A inverse B. Okay, so again, this is, let's imagine this linear system here, right? If A is non-singular, I know that there will be a solution, vector x, right, for B, right? A unique solution at that, right? And since A is non-singular, right, theorem NME tells me that there exists a inverse. It is invertible, right? So this is IN. And again, this is some product here. and the identity times this vector x. Remember, this is n by n. This is n by 1, so that operation is valid, and the identity just yields back that same column vector. And we could see that it gives me a way to find the solution to the linear system, right, by using matrix multiplication and not row operations.